So, just recap just to get a speed, we have been away for a while. We are looking at box models for pollutant transfer in air. So, essentially this is generic box model. For air we are looking at these are the processes that we are considering in the box, the advection, dispersion, reaction, exchange and all that. Okay. So, the specific problem for air is that the height is not very well defined. So, we look at what is called as a mixing height, and mixing height depends on this concept called stability, and the stability is a function of temperature in the lower atmosphere, and we looked at stability as this stability is the behavior of an air parcel when it originates somewhere in the near the earth's surface and then it travels upwards, and then what happens to it. So, the ideal case of that is called as adiabatic expansion from cooling as it goes up. So, this is the summary of that. So, the atmospheric stability is the behavior of a parcel in conjunction with its environment, whatever is there. So, the environmental lapse rate or the temperature gradient in the environment that exists at any point in time. So, this figure shows the change of the environmental gradient, one example. Okay, it is not, this may not happen all the time, it depends on the place and time, the season. But the adiabatic lapse rate from a particular process stays there, it does not change because its source temperature at the ground is wherever, whatever it is, the temperature of the emission, whether of an exhaust or of whatever process that is happening. The atmospheric stability is the lapse rate represented by gamma. The adiabatic lapse rate is given as minus 0.0098 centigrade per meter or 9.8 centigrade per kilometer. This is the adiabatic lapse rate. This is the dry adiabatic lapse rate, and this is the derivation of that. It is there in many textbooks. The nomenclature varies, but we have tried to so you can go through this. This is basically two things. One is the static change in pressure is rho g delta dz. This is static pressure definition, and this is the first law of thermodynamics, which means it is an adiabatic process which is dq is 0, dw equals du. So, it is minus of pdv equals mcvd. It is an ideal, it is based on ideal gas law and all that. So, you can go through the derivations, fairly straightforward, and then we use the definitions of Cp, Cv and all that. We come to this point and then we come down here, we get dt by dz equals minus g by Cp. Cp is the specific heat of air, dry air. So, if you insert these values here, you get minus 0098, but the actual and this also has assumptions that when the parcel is moving up, there is no heat transfer, it happens very quickly. So, there is no, that is the assumption of adiabatic this thing anyway, that it is insulated. So, there is no effect of, there is no heat transfer from the surrounding thing, there is only buoyancy effect, that is all. So, the density is changing based on the this thing. There is another term called potential temperature. It is defined like this, theta equals T0. This is the temperature corrected to particular pressure. So, the pressure with reference to sea level pressure. So, it is the temperature of an air parcel at temperature T1 and pressure P1 if it is moved from to a pressure to a pressure P2. So, it is similar, it is corrected temperature to pressure. So, just like dt by dz, you can also call theta by dz, and the definitions are given. So, these are the more theta is the more normalized way of handling it. In many textbooks you will see theta rather than temperature, but for practical considerations temperature gradient is what you will be looking at when you look at heat flux. So, you look at the lapse rate this way or this way, the temperature gradient immediately will tell you whether it is an inversion or not an inversion and what is the value of it with reference to that. So, this we did all this to define stability, and we also looked at the this concept of mixing height, mean mixing height as the function of the place where the intersection of the environmental lapse rate and adiabatic lapse rate happens. And so we also defined that this is a plume, the boundary of this thing. So you can say within this a lot of things happen. The plume may go in and out, but there is something called as a time average plume. So if you keep looking at it for a long period of time, there is a shape that the emission takes, and that's called as a plume. And we looked at different shapes from the thing. So this is redesigned, redrawn again, and to explain some of the things for each of the different types of plume shapes that can. This is a limited set of plume shapes. You can have a large number of plume shapes based on various combinations of the environmental lapse rate and the plume and the source height and all that. So this is one set of conditions. But if you know how to the basic fundamental aspects behind it, you can predict what is the plume shape that you can expect for a given situation. So there are different kinds of plume shapes that you can expect. So last time when we were looking at the pollutant transport. Our goal is to be able to predict concentration as a function of space and time, x, y, z and time. So we look at one control volume within the plume, which is where the pollutant is moving, and we try to model it. So this is we did this last class. We will go over this once again. So if you take this box which has dimensions of delta x, delta y, delta z, we have this term here. Rate of accumulation equals rate of in by flow, rate out by flow, rate in by dispersion, rate out by dispersion. So these are the processes we have identified. So before we write the equation, we have to figure out we have to determine what are the processes that we are considering in the system. So the transport model can have anything. The generalized transport model will also have reaction, will also have adsorption, will also have deposition, all these things will happen. This multi-phase model. But we are not doing that here. We are looking at only rho A1. So rho A1 is gas vapor phase concentration only, okay, and we are not even looking at rho 3.1, which is the particulate matter. We are only looking at rho A1. So, but this gives you an idea as to if you want to do a very complicated model, you start here. In this thing, you add processes here. So I can add other processes. I can add other processes here in this equation, and then from here you derive the differential equation that you need to solve. The solution of differential equation is a different issue. That's a mathematical part. So then, to make the mathematics solution easier, we make more assumptions and make it easier and all that. So that's a different section. So from this point of view, from this class point of view, you need to be able to write this equation, and then somebody else can solve it. That's not an issue. It's okay. So because you need to understand what are these processes and how they happen, whether they are important or not. So rate of accumulation, rate by flow. So what we mean by flow is the wind is bringing it and taking it away. Dispersion is a different process. Dispersion is happening because of buoyancy, it's because of the convection, wind driven convection and anything else. So these two are the processes which we have said. So you can add other reaction and all that here, but in this case we are going to assume this to be 0. Okay. You write the balance always for one component. So in this case we are writing it for this particular A in the phase that we are interested in, the vapor phase only, because this is a phase we are interested in calculating exposure at some point. What we are interested in this case is that, say I am interested in this person standing here on the ground, and what is the concentration that is you are being exposed to. Okay. So from this point of view, I would like to know if this plume is going to travel to this person. It's standing at a distance of 5 kilometers or someplace, so some distance. Or if there is a building here and this building, somebody is living in this building, the plume is going to intersect it, what is going to be the concentration at here. So these kind of things is what we are interested in calculating. So, okay. So in this equation we write this rate of dispersion, this is a flux term, this is flux multiplied by area. So this flux here is given by Na equals minus dAx, We are going to drop the A because it is A that is going to be considered next few slides. We are only looking at A, there is no other component here. So, it is just dx. This is a Fick's law, this is an equation that is based on Fick's law. So, we will, those of you who are not familiar with Fick's law, we will come back to it later after this section. But it is a very generic law for diffusion, it is a very common kind of equation that we see, this form of this equation for any flux. Okay. So, for now take it from me that this is the structure of this particular term, we will come back to the fundamentals of that later. So, we take that equation and start adding all this and dividing by delta x, delta y, delta and setting the limits of all of them to 0. So, first thing what we are doing here is we are only doing it for x. I have not done it for any other thing. This equation will become too big to write for all components, but for writing for x only I am writing this, so I will get this. Similarly, if I extend this to y and z as well, so y and z directions, this is a mistake there. So, we only have, when we are writing this previous equation, we are only writing the rate in by flow is only in x direction. We know that already, there is no flow, pressure driven flow in the y and the z direction. So, only x, but these two terms can be in all three phases. Okay. So, that is what we are writing here, we are writing this extended term. So, we will write these three terms in all three dimensions. We will write delta Na by delta y, delta Na by delta z terms also in this case. So, that will become, so there, if I am only doing for one x I get this equation, if I do the others I will get this extended equation. We have dispersion in all the three directions. This is where we stopped last class. Now, here we make two assumptions, one is a steady state assumption. So, you do not have to do this, but for the Gaussian dispersion model that we generally present, we use the steady state assumptions where we say rho a dou rho a1 by dou t equals 0, which means that at any point in time the concentration is the same, you at any place, any location you measure, concentration will not change with time, but it will be different with space, but it will not change with time. Okay. So, in a plume, if you are looking at it in a plume, nothing is going to change. So, which means for this to be true, everything else has to be true. The emission has to be constant, the properties have to be constant, nothing should change with time. If any of the parameters in this model changes with time, then this is not true. You cannot use an unsteady state assumption. So, which means it is an assumption, in the environment nothing is constant, everything is changing, which is why we use average values and then we use standard the variation, and then we see if you use the average and you use the variation, what is going to be the range in which these values are going to be fluctuating from, and that therefore we make our decisions based on that. The second thing that we do is, since we already have ux bulk flow in the x direction, we neglect this dx term. So, this entire thing reduces to this simpler equation. This is where we stopped last class. Now, the general solution for this is an equation, there are solutions are already there, this form, you do separation of variables and do all that, you will get an equation of this form. So, there are multiple constants that will come out, there are C1, C2, C3 because there are 3 dimensions here, the x is there, y is there, z is there, there are multiple things. So, we club all of them into this constant, everything comes into one constant, and then we use this, people use this single equation as combination of all the boundary conditions. Okay. So, normally when we say boundary condition, we will say x equals to x1 value of rho a is this much, or something happens to it, there is no flux, there is a wall boundary condition and all that. We fix the values or we give some indication as to what it is. Here we are doing all of that in one shot, and what we are saying is this using a mass conservation in the plume. If you take the entire volume of the plume, the entire volume is coming from the source. So, we are saying that Q is the rate of pollutant release equals U multiplied by dy and dx. Ux into dy into dz will be, if you look at the dimensions, it is L by T into L into L into m by L cubed. This is m by L cubed equals m by T. Yeah. So, this q, and so we are integrating y from minus infinity to plus infinity, which means this is the y axis, this is the x axis, this is the z axis, and this is the y axis. So, there is a plume that is originating, let us say here, and it is going here. It is expanding in the y axis, it is free to expand wherever it wants, y axis. In the z axis, it is not free to expand wherever it wants, there is a limit, it has to stop at 0, because that is the ground, it cannot go beyond that. So, that is why the limits are 0 to infinity. Above the ground, it can go however long it wants. So, the plume boundary is fixed in the y direction by minus infinity to plus infinity, when x are in the z direction. In the x, it is anyway moving, and this is set by this term ux. Okay, so, it is the rate at which it is moving, and that the rate at which, so the plume boundary is expanding in the x direction and in the y direction and z direction. So, overall boundary is now the total amount of mass present in this plume equals q. Okay. If you use this, the constant now is determined as this q divided by 2 pi dy dz raised to half. You substitute it back into this equation, this is the general solution. So, this you get is the general solution. Okay. Now, here this general solution is you need this term dy and dz and all that. So, this is all important. So, you can use this equation as it is, but there is something that people have gone ahead and manipulated this particular equation with the ideal assumption that if you look at this equation, this is very similar to another equation which is called as a Gaussian distribution or a normal distribution. So, where the equation for normal distribution is this, f of x or y equals 1 over 2 pi sigma into exponential of minus of x minus x 0. So, this is x 0. So, in this is a distribution this is x 0, it is the mean value. At this value, what is the value of at this x 0 is the value of f of x is the maximum. So, it is a symmetric bell curve, okay, and the spread sigma is the spread, this spread, and the value of the spread at 60%, some value, some percentage of the mean f of x. The magnitude of the sigma indicates how much of spread there is. So, if more spread, because of conservation we are assuming that if it spreads more, the highest concentration is going to be smaller. If it spreads less, the highest concentration is going to be higher, which is consistent with our this thing that if a plume is confined to a smaller volume, concentration is likely to be higher. If plume spreads more, the highest concentration is likely to be lower. So, where do you find the highest concentration? Where will you find it? So, for which we look at an ideal plume. So, an ideal plume is like this, it is nicely going in this cone kind of fashion. The cross section looks like an ellipse or even a circle, some form of ellipse or a circle. So, in this, if you look at the distribution of pollutant concentration, so concentration distribution. So, if I am plotting, instead of this, if I plot instead of f of y, what I am plotting is rho a1 as a function of z or y, either, I am likely to find that this concentration will look like this, which means at some value the highest concentration occurs at some value of z or y. Yeah. So, let us say this is z and this is y. This y dispersion occurs like this, z dispersion occurs like this, depending on the how much of dispersion is occurring in the y and z directions, that is different. So, these curves here show the dispersion, the spread of the distribution of the concentration. So, it goes to 0 outside the plume, at the plume boundary it stops, the concentration goes to 0. Somewhere in the middle of the plume right in the center point, it is the highest concentration. This is an idealized curve, you have to understand that this is an ideal curve. This does not usually happen. A lot of times this is not like this, it is a bit skewed and all that, but this is a good starting point for a lot of these kind of things. So, what people did is to fit this equation into the format that we have. So, this equation here does not look, it looks almost the same, but it is not in the same format. So, we are fitting this into the same format. So, which means we have to define some new parameters to fit this equation into a format. So, this is the Gaussian equation. If you look at the bottom equation here, the Gaussian dispersion model looks like the other equation, except that there are a few other additional terms here. Now, to make it look like this, you have to do some transformation. So, one of the transformations is this one and this one. We do sigma y and sigma z into 2 dyx divided by ux and so on. So, you make these transformations and we enforce that the concentration at y0 and z0, these are the points at which the highest concentration occurs, which means this is the center of the plume wherever. So, this is the value of y at which the highest concentration occurs, this is the value of z at which the highest concentration will occur. So, this depends on the source itself, this depends on the shape of the plume and where is the source and all that. So, if you have an idealized this thing, so if the plume is going like this point, this line in the along the x axis, on top of the x axis will determine what is z0, because this is the center point and we are looking at the concentration, the distribution of along this will be like this. So, at this height you are going to get the highest concentration. Similarly, if you look at this from axis from this side, okay, if I am looking at it from the y direction, this is the y axis. So, I have, right, but again along the x axis, because this is a plume, this is called as a, and the x axis is called as a center line where the y is 0, is there some height, at height z equals to 0 is the highest concentration, but also at y equals to 0 the highest concentration occurs here. Okay, so, this is y0. So, in this particular case y0 is on top of the x axis. Okay, if you look at it, if I flip the axis this way, if I am looking along the x axis towards the source, it is along the x axis, it is on top of the x axis, which means y is 0, that is the center point. It could be anything. So, it depends on how we are defining the coordinates and all that. So, we will come to that later, when that will become important. So, this is not a, there is no general reference, you have to take a reference point. If you take the source as the origin, from there everything else is defined. That is why it is the Lagrangian concept of this model is that there is no fixed reference point, there is no universal this thing, it is with reference to the plume itself and the stack itself. So, so this final equation looks like this. So, the Gaussian dispersion model in its preliminary form looks like this equation here. Now, when we input this y minus y0 x minus x0, so if the plume if the stack source is at the origin, this x equals to y x, this is y equals to 0, and there is the height of this emission, the stack. So, let us say there is a chimney and this goes to a certain height, and that is where the emission is occurring. So, you expect the highest concentration to occur at that point. So, therefore, here in this case y0 equals to 0 and z0 is the height. So, therefore, this equation modifies itself and becomes this z minus h, where h is the height of your source. Now, sometimes the source need not be in a chimney, it could be on the ground. So, that time h will be 0, which will become then that equation will modify further. Okay, so, you can modify this equation whichever way you want. So, this is a general equation. Since we have now, I would recommend starting here, because there are a lot of cases in which you will not have a stack, you will not even have y will not be defined as the x axis, it may be separate, but most often y is the center line, that is the center line. So, do not worry about that. The second thing that is important here is the x axis itself is defined as the direction of the wind speed. X axis can change wherever it wants, it can point north, it can point east, west, south, does not matter. In the reference of the Gaussian dispersion model, x axis is the direction of the wind. So, the wind speed keeps changing over. If you look at Chennai for example, the wind speed is in the morning in one direction, in the afternoon it is in a different direction, it keeps changing with season and all that. So, you cannot have the wind speed, you cannot have fixed frame of reference, the frame of reference is with the wind speed. So, you have to find out what is the wind speed and then start there, and then the rest of the axis is defined, y axis is defined based on this. So, there is no fixed x axis, okay. This is very important. So, the first thing you need to start all of this, you need to know what is the wind direction.